All right, welcome everybody. Hope that things are going well for everybody. Today I have the distinct privilege of speaking with the Eigenbros, and we'll be talking about all things that are relevant to the three of us and the rest of the world at large. So thank you, gentlemen, for joining me today. I appreciate it.
Yeah, well, thank you for having us.
Why don't we start with a brief introduction? Who are you, and why should everyone who's watching or who watches subscribe to your podcast, aside from the fact that you have a podcast? Did I just spoil everything?
No, not at all.
No, not at all.
So, well, we have to put out some news, unfortunately, that the podcast is actually coming to a close soon.
Well,
so
it's more of an evolution.
Yeah, an evolution, but we still want you to join, of course, subscribe. Yes. But Juan has recently just gotten a job, so we're winding down. The man is making money. He's doing big things.
Yes.
So me and Juan's content are evolving here. So we're gonna have a little bit, maybe a different thing going on in the future than podcasting. Maybe just putting out science content in general. Mm-hmm. But my name is Terrence, just to start off with, and we've been doing this podcast for like what, 3-4 years?
3 years.
Yeah.
Yeah.
And we're our background is physics.
Yep.
Condensed matter physics.
Experimentalist.
Yeah. We actually do real things here.
Mm-hmm.
Theorists.
Yeah. And so we both are physics background. We met in graduate school.
Right.
And
so your name.
Yeah. Oh, my bad. My name is Juan.
Juan. Juan and Terrence.
Yes, indeed.
Yes, sir.
So where did you do your undergraduate and graduate work?
Well, we don't like to disclose that.
You don't disclose that? Okay, fair enough.
We don't like to, but we are in Florida, we will say.
Yeah.
So figure it out if you want. There's not that many
if you could
places to go.
I'm sure there's some listeners that have guessed already.
Yeah.
I'm sure
there's some people that have guessed. Yeah.
But for the for sake of I guess just more privacy, I guess.
Yeah, no problem. Hey, that's fine. But I'll tell you where I went.
Yeah, sure.
So I did my undergraduate at Podunk State University.
Okay.
It was just up the street from my house, so I got to live at home in the basement. And well, I wasn't in the basement, but it was effectively in the basement, living at home as an undergraduate. I went to Weber State University, which is where. So for those who have done like astronomy, the Big Orange astronomy book, the authors of the Big Orange astronomy book were from my institution, as well as Peskin and Schroeder. So Schroeder, who did the thermodynamics book and Peskin and Schroeder book, he was also one of my professors.
Wow.
That's the QFT guy.
Schroeder?
Yeah, the quantum field theory book.
Schroeder, that's the classic that we used in our school
back in the day. And so I didn't have any idea that they were much more famous outside of campus than they were on campus.
Interesting.
And then from there I went to the University of Washington to graduate school.
Nice.
And I was in physics there, and but most of my work was actually on the astronomy side. So you said that you're both condensed matter. What did you do in condensed matter, and how did you get into that?
So I guess my background. I guess I'll give my undergrad. I went to University of Texas, in my hometown as well. Mm-hmm. Not living in a basement, but effectively physics kind of forced you to build a cave. And yeah, so they in that school, we were a big material science school, and so that helped me gravitate towards condensed matter in some way. I was always interested in quantum systems and quantum materials, so naturally I went towards that. Unfortunately, my undergrad institution didn't really have the kind of how would you say, experimental condensed matter that I wanted to do.
Right.
Which was more...
It was a little bit lacking.
Right. It was more focused on surface level materials characterization and that kind of aspect.
Yeah, that's... we actually brought in someone who did condensed matter, and that was essentially what they did as well. Although my undergraduate, they explicitly chose as a department that they would not have a graduate program. So about a few years before I got there, they had a vote, do we want to add a master's program? And they're like, no, let's just stick with undergraduates all the way. And so
interesting. Why that is?
Um,
just didn't feel ready for it, I
yeah,
guess.
the faculty, there wasn't quite enough faculty, and they felt like it'd be better for them to do a good job at the undergraduate level than to do a mediocre job at the master's level.
That's smart.
And it's been, I was really happy. I mean, I kind of backed into it, right? I had no idea that I would be as fortunate as I was to go where I did at the time that I went. So
Nice.
I did some laboratory work, but it was, they're still working on the project that I was working on 20 years ago. So like, oh, you should see what we did with your setup.
So what was your background was, your lab work, was it mainly focused on like building certain things? Like what was the discipline, I guess, that they had you in?
So I did, as an undergraduate, the research that I was technically involved in was rubidium, like atom trapping. So this was right after the Nobel Prize was given for Bose-Einstein condensate. And immediately after that, there was a paper in American Journal of Physics where someone said, here's how you can do Bose-Einstein condensate in an undergraduate laboratory. And so that was when half the country all of a sudden became condensed matter physicists doing Bose-Einstein condensate off of that one article. I mean, that was probably one of the most, there were probably millions of dollars spent because of that one article about how you can do this in the laboratory.
Yeah.
And so I started on that. And then it was basically that end of that year when maybe I did a year and a half before I started graduate school. So it was kind of good experience machining. I machined a bunch of parts. I didn't really work with the lasers or anything like that.
Well, in my first year of undergraduate, I did a lot of machining of waveguide.
Nice.
Mm-hmm.
Very boring.
Yeah, no,
I was like, this is not what I signed up for.
Yeah, that's how I felt about materials characterization, just because it looked so appealing. It's sort of like, just like, wow, look at all the cool stuff you're doing in condensed matter.
Mm-hmm.
And at the time, I started undergraduate in 2009, and so in that my whole career in undergrad, I was building up towards condensed matter, just because they didn't officially offer it in my undergrad. But when I got to graduate school, it was, I mean, I had access to a lot of resources, way more resources than I did in my undergrad. And that's where I learned how to be a better condensed matter physicist. My background in particular, I guess Terrence can find some intersection here, but it was fabricating devices.
Mm-hmm.
And then particularly for me, it was a cradle to grave approach. So it was, sort of synthesizing these elemental precursor compounds straight to like building the crystals themselves or synthesizing it themselves. And then from there, we call it the Scotch tape exfoliation method.
Uh-huh.
Yeah.
Yeah, everyone does that, right?
Yeah, everyone does that. There's no other fancy name to have it for, but it's
like, we need one layer of carbon atoms. Okay, lay it down,
exactly.
Feel it off. That's
exactly
as good as it gets, though, man. You've got to love the simplicity sometimes.
Uh-huh.
Yeah, and I mean, yeah. So I worked with van der Waals compounds in my graduate career, and just helping build a bunch of those with some devices. And I got lucky with a particular compound and published a couple papers, got a couple more coming out. And then I moved on to not industry, I guess government lab.
Yeah.
Yeah. So
yeah,
they're
right
not
now
quite
I'm-
the same.
no, not at all.
To some faculty members, it is the same. It's like, oh, if you don't make it like I did, then you can work in a government lab, as though, it's like, I worked at Fermilab, and the environment at Fermilab was definitely, I mean, it was physics on steroids, the way that it operates there, in terms of every conversation was about physics, every lunchroom discussion was about physics. It was all physics all the time. And so there are a number of people that, if they actually knew what government labs were like, at least where I was, they'd be like, oh, that actually is quite the academic environment, like stimulating environment for physicists.
Oh yeah. Oh yeah, I mean, there was kind of how would you say, some infighting, I guess, in between
Ooh.
in between departments and the lab, just because there was a student that said the students that work at the government lab work much harder and are expected to do more.
Are you talking about at our graduate
At our
institution?
graduates, yeah. And somebody in the faculty was like saying, "How dare you?" They work
That's a shot
just
to the
as
ego,
hard.
man.
It
You
is
can't
a
keep
shot to
throwing
the.
that
You
out.
know what? I will say, maybe it's a little bit harsh for the other student to say that, but
They're right though. It's true.
but the perspective of somebody who works full time in a government research lab, that's literally all you're doing. You're not teaching. You're not doing anything like that. So research and physics is on your mind all the time.
Yeah.
Yeah. So yes. And that's pretty much it. I mean, I just that's kind of a good synopsis. What about you, Terrence?
What was the question?
Your background in physics.
Oh, background. Yes. So so my background is condensed matter. I've been doing it since the beginning of my physics career. As an undergrad, I did machining, you know, as you did as well, Jason. So we have that in common from the beginning. And then I went on to spintronics. So that's like fancy stuff for trying to utilize the magnetic moment of an electron to basically, communicate signals. So like, you know, how we use current for a lot of things. I mean, for pretty much all electrical signals now, so I guess maybe light. So spintronics was supposed to be an answer to using electron spin to kind of, you know, send signals, store data. We even use some of it in phones already, like giant magnetoresistance is something that's related to it, spin valves. So that was really cool. That was kind of what cemented my journey into condensed matter. And then I went to another spintronics group in graduate school, did a lot of fabrication like Juan. I mean, we had very similar projects. We use a lot of the same kind of equipment. And well, not similar well, I guess it's kind of similar project in the sense that it's device fabrication. And and then I, you know, built some devices, semiconducting devices, and got to learn a bunch of cool machinery like SEM, scanning electron microscopes, you know, ion mills, evaporators, all this cool stuff. So that was pretty much my physics journey, I guess you could say.
So what was it that got you into physics in the first place? So my background from high school was I cared about band, and that was it. Everything else was like last place. And my least favorite class in high school was my physics class. I did not like that high school physics class at all. I got better, but it took an astronomy class as an undergraduate to like kind of pull me out of the funk, because I did not care for physics. I thought, you know, maybe I'll be an engineer and design airplanes, but they didn't have engineering, and I had an astronomy class, and so that's how I got into it. What was your trajectory into getting into physics? Mine was not inspired from a high school teacher.
Yes, I think we have a very similar tale there in some sense, except I didn't even know what the heck physics was until undergraduate in college. So I was an orchestra guy, heavily obsessed with music and orchestra, violinist. I've been playing violin for like 20 something years. I don't even know how long anymore. But yeah, that was definitely my top thing I was interested in. But I always had this kind of love for math and science, some weird way, even though I did not do well in math at all.
That was my lowest grade.
Same. I mean, I retook probably every math class every single year, at least once. I took algebra probably 3 times. I failed it twice, I think. So yeah, but the weird thing was, the dichotomy was that I was writing programs in class pretty much every day on my calculator. So I just didn't know that I actually liked math. It's kind of this weird thing, right?
Yeah.
So once I understood kind of the utility, you know, when I landed in undergraduate, I got obsessed pretty much with Michio Kaku. You know, Michio was my guy. I loved Michio Kaku and Neil deGrasse Tyson and Brian Greene and who else? The real Brian Cox, you know, like all these real pop sci physics guys. And I just started going down the physics rabbit hole, and I was like, you know what, this is really cool stuff, and this is like the kind of career that I've always dreamed of having. Like I didn't know you could just study the universe. Like I had no one in my family, no one around me knew anything about physics. Like no one ever really talked about it. I had no idea what it was, so I didn't even know this was a career option. And I really only discovered it, once I started watching, Discovery Channel and History Channel and all these educational channels to really enlighten me on what it even was, and that kind of started me down on that path.
Mm-hmm.
Yeah, that's inspiring.
Juan, what about you? Did you have a similar thing? Except for you, it was also drumline.
No, I wish I was that cool. I was. I literally didn't. I took physics in high school, was also one of these classes that I didn't pay attention to. I somehow managed to get to calculus, but admittedly I wasn't good at math. I sort of was attached to one of my friends who was good at math, and so I would like do homework with him, but at the end of the day, you couldn't ask me what an integral was.
Right.
I'd be like, I really don't. I'm
that
just
S thing, you mean?
Yeah. It looks like a musical note.
Yeah.
And so, I took it sort of seriously, not really. I was more preoccupied with just generally doing good in classes, without really understanding what I was doing. But I always loved science. I was really good at biology and chemistry. But physics was one of these things that was done a disservice, really.
Yeah.
And so
high school doesn't seem to be the place to do physics. I read whenever I look at the high school physics textbooks are just like, so it's all kinematics. Here's the angle and here's the ball that's moving in it's projectile motion, as though that's like the most interesting thing that's ever, crossed the desk of a physicist was, let's look at billiard balls colliding on a surface.
Yeah, I remember there's a couple memories implanted in my head from this physics class. One of them being, this stuff is so boring. Who would ever do this? And then
for a job.
It's on you.
Fast forward 10 years later, bloop, I'm talking about physics on a podcast. No, but the other thing is there was a really cool lab setup that they did with optics and lasers, and that blew my mind. I don't remember the exact experiment, but I think we were calculating the speed of light or something, and it just blew my mind how you could build such a thing. And there was some.
Was it chocolate bar?
I don't remember.
Okay, that one was cool when I saw that one.
Yeah,
you could calculate the speed of light using a chocolate bar in a microwave.
Yeah,
that's awesome.
I've never done that one. I should probably try that one just to see if it works.
So cool, man.
I have to take
so cool.
So is that something that I look at high school curriculum and I'm like, okay, this should change if we really want people to be interested in it. Because there's a lot of stuff, both in physics and math. So when I was an undergraduate, I did both physics and math as my majors. And I remember getting into modern algebra with group theory and the symmetries on different shapes and things like that. And I was like, they should teach this in third grade. There's no reason that a third grader can't be like, hey, look, I can solve interesting things with these, look at interesting properties of rotations of shapes and stuff like that. But no, we save it for after all the attrition of fractions and equations and everything. And then you get all the way to your senior year in college. And then we're going to teach you the cool stuff.
Right.
Yeah.
It's like weird because all the stuff that I feel like, all the cool stuff, it's weird because all the people who are good at math, I feel like, in elementary school and high school are not the kind of people that you really look at as the people who really accelerate in physics and math at the highest levels, because it's such a creative endeavor.
You're saying on a curve? I mean, because there's Terrence Tao.
Right.
But he's a prodigy.
Yeah. But he also got exposed to the cool stuff early is what I mean.
I
so
see.
What I'm saying is like, when you are good at just doing multiplication and addition and subtraction and all that stuff and like the rote kind of like
computation
calculating process, that's not really interesting to creative people. And I feel like that's why one of the reasons why a lot of creative people don't even consider or even look at physics or math really
Mhm.
in the early stages, because we're like, who gives a damn or crap, you know, because we're like, we can use we can use a calculator or whatever we want. It's like,
well,
it's
and
not really
then you get the wrong impression, right? You get caricatures in the media about like, oh, physicists, they really care about how hard should I hit this volleyball to get it over the net. It's like, no, physicists don't actually care about that at all.
Right. There was a meme on the internet that I saw that was like, how fast do you need to slap a chicken, or was it how many times? I don't remember.
Oh, to raise
to raise the temperature of a turkey, something.
Funny,
that is a physics problem, but it captivated the minds of millions probably. But there are these like, I think you nailed it on the head. We're saying like, we're not doing a good job of captivating the imagination of a lot of people when these topics are super interesting. I mean, well, I think we should market it more into a conceptual thing. Maybe kind of have it be, here's, you want to learn some cool stuff, sort of, kids are passing by the hallways, we should always be advertising.
Right.
Mm-hmm. Particles can tunnel underneath, barriers and whatnot. You just kind of try to show them the cool stuff, black holes and quantum mechanics and stars and planets, star formation, where you get elements from. I mean, a lot of this stuff just gets, how would you say, just thrown to the wayside because
just nobody even talks about it. It's like, if you just ask someone like, how old is the universe even, like that could be such a good starting point to so many interesting questions, I feel like. And it's just such a backwards endeavor. Just like, Jason, you were saying, like, we're just looking at inclined planes and pulleys and whatever. And it's like, all right, it's fine. But like, it's such a minimal part of really the crazy cool stuff you can actually figure out with physics. Like, it's such a world that's so interesting, that it's really a shame how it's so unknown until you get really to the higher levels.
Let me add to this.
Yes.
It's like somebody showing you a Ferrari, and then you go on the inside of a Ferrari, and you have to do the Flintstones pedaling. Like you have to, and I think that turns away a lot of people. Because,
I thought you were going to say like showing you a Ferrari, but when they take you in the Ferrari, they just show you like the cigarette, what was it? The cigarette lighter. Yeah. Like none of the cool stuff about the Ferrari, just the stupidest part of the Ferrari.
The doors lock. Look, I can push this button and the doors go.
You have to put the window down with the
with a hand crank.
The hand crank,
right.
Yeah. There's a very attractive stuff. So we have to kind of integrate these things into the curriculum where we know you need to know how to do physics if you really want to do it, but also keeping it fun.
Interesting.
Yeah.
Mm-hmm. I've been working on some kind of professional development stuff for the local school district. And I've noticed, so the next generation science standards is kind of the new thing, and it's supposed to be, and when I say new thing, it's like 15 years old or something like that. But it's supposed to be driven by phenomenon where you look outside and you say, okay, the sun is shining. How does the sun shine? And then you learn physics based upon, here's something I'm trying to explain. So you're supposed to, the idea is that you provide some motivation for why you would care about this stuff. And you go from there. But I'm looking at some of the standards, going through it to see, what is it that the people are supposed to learn at different grade levels. And I have to admit that some of it is also kind of the boring stuff that it's not like the real beauty, like the deep physics things, Noether's theorem and conservation laws, and where, the electric charge comes from this conserved quantity that's associated with the invariance of the quantum wave function under rotations of the phase or stuff like that. That gets completely left to the side, which, I mean, I guess it doesn't have as much practical application, but it certainly has the awe factor, the wow factor, where students be like, I had no idea that, this whole thing works because of this one mathematical property. Like the connection between math and the real world is something that honestly I didn't really even appreciate until I was halfway through graduate school.
Right.
Yeah. No, for sure. I mean,
Yeah.
I really didn't feel the connection until I started learning calculus. That's when you really saw the bridge between physics. Some people would say reality, I guess, but the bridge between physics and math was calculus in a lot of ways, and it was sort of an awakening, I guess, for me. I don't know if you feel the same way, but because algebra feels very geometric, right? I mean, a lot of the roots are
feels
in
really
Pythagoras. Yeah, I guess you're right. But I mean, like, the roots in geometry are very are instilled. I mean, you have Pythagoras theorem.
Yeah,
you have a lot of these things.
It's like algorithmic, that you just like, here's the process that you go through. And as a consequence, like, you learn how to do calculations, but you don't learn any of the depth as to why these things work the way that they do, and what are other properties of numbers that, in sets, different types of numerical sets, like the Cantor set, or things like that I think would be really interesting. If you go to a sixth grader and you tell them, hey, you can do this to a set of numbers, and you can get as many numbers left over as you started with, and yet you've pulled everything out. Those kinds of things really can blow people's minds. I remember doing something for like a Cub Scout group or something like that, where you take a piece of paper and then you twist it, you make a Mobius strip, but then you twist it one more time, and then you start cutting it and seeing like what happens if you take a strip like this and you cut it down the middle, and then things come apart, or you make one big long one. And just those kinds of simple manipulative math concepts, people don't recognize it as math. But even knots, like tying knots, if you pull it this way, you get this kind of knot. If you pull it this way, you get a different kind of knot.
Right.
And even probability. I mean, there's we were out at a bar one time, and a friend of ours, a fellow physicist, gave us a cool little puzzle about how do you guarantee, it's like two people in a prison cell, and you have to guarantee that both of you will come out alive if you can guess what was it, the probability that I guess a coin flip. Do you remember the riddle?
No.
But essentially,
I think you're messing it up.
Well, it's but the guarantee is you have to kind of have a firm understanding of probability. But even when you get it, it's sort of a eureka moment where I can imagine these kinds of like problems that would feel like real consequences and interesting stories. Can be rooted in math tricks.
Like the Monty Hall, like, here's 3 doors and you pick one, and then they open up another one, and do you change your mind? And so in your experience as social media science influencers, what have been the things that maybe have been surprising in their ability to connect to people who haven't been in the science before, or haven't necessarily previously been interested? What are the gateway drugs that we can use to pull more people into physics?
Oh, it's a great question, man.
Oof, I think
but we're nowhere near, I don't know if we're really as qualified to speak, like.
Well, you know what? I was just flattered, so I'm going to entertain the question.
All right.
I would say, I have a problem with Schrodinger's cat. Let me just say that.
Yeah, I do too.
He's rolling his eyes, but that one's a great example of something that can pull people in when people, and it's part of the vernacular now, right? People say, Schrodinger's, like, whatever you want to say, like when people say yes and no, right? It's thrown in the vernacular. That's a great advertisement for physics, which is
the only problem I have with that. Just a little caveat is that people always say wrong stuff surrounding it. So I really kind of am touchy on that one, because talking about quantum is always a losing battle. But anyway, continue on one.
Okay. So I do want to say that things like that capture the minds of a wide audience of people do better for physics in terms of putting it on the map, and increasing the visibility of it. And physicists need more of those interesting thought experiments.
So astronomy has it kind of easy because we can just take a picture and be like, look at this, isn't it amazing? And people say, wow, that's amazing. And then so
the scale. Yeah.
The high energy physicists really, it takes more thought to bring high energy physics to the same level of like the same wow factor that you get with astronomy.
Right.
Yeah. Because
they got a little media team, with the whole God particle whatnot. So they're trying something.
Right. Yeah. CERN is, it's like I like to say CERN is like the Los Angeles media of sports. It's like they're always, they're
just like killing it with the media. You think?
Right. Yeah.
Yeah. They put out good videos, high quality stuff.
Right.
They're doing an all right job.
Mm-hmm.
But I agree with you in the sense that they don't do a good job of selling it to people why it's important. I've seen pictures of the CERN, the high particle, what is it? The diagrams of man, I can't believe I'm blanking.
Like where they show all the particle explosions,
right?
And you see all the particles in like
the tracks that you get in the detectors and stuff like that.
Exactly.
Yeah, I've seen that, and I saw that before I even knew what high energy physics was.
Yeah.
It was on a cover of the Strokes.
Oh, really?
I think, Is This It album?
Oh,
it was one of the album covers.
Oh, that's cool.
And I was like, oh, that's a cool cover. And it turns out it's from the CERN data. But the thing is, most people aren't going to know what that is. You have to sort of tell them why you should appreciate it in some ways, which is, it's sort of like explaining the punchline of a joke.
Mm-hmm.
It's like, you can't.
Yeah, there's definitely some truth to that. And a lot of things, I will say that even not just speaking about the philosophy or the metaphysics of quantum mechanics in terms of, I've never really been interested in, is dead end, Schrodinger's cat wanted dead end alive type things. Is the Copenhagen interpretation the correct interpretation of quantum mechanics? That's not my shtick. Okay. But the things like, what is a W? Like, how does the W and the Z particles, how are they similar to or different from photons? And what is it
called forces?
Right.
Like that still, I don't know if I have a good answer for that, because when you start talking about the W and Z bosons and you start talking about, that's a weak force. I remember when I was, just getting into physics, I was like, what does that even mean? Like, why is it a force? Like, is it exerting some, so I don't have another word, I guess.
Is it pushing on something?
Force on something, yeah. But it's not. It's weird. It's like, that's when you start to get high level enough to where you're like, that these names start to even kind of transform to mean multiple things,
Well, I think about this all the time. In fact, I'm still trying to come up with like, what is a good generic explanation for what a force is. So my current, definition that I'm operating from is a force is a way to transfer quantum information from one object to another. So you have these two objects, they can communicate to each other through one of the forces, and then when they do that communication, they're actually transferring quantum information from one to the other, or quantum properties from one to the other. So you can transfer spin through the emission of a photon. You can transfer momentum or energy through the emission or absorption of a photon. And so the force is just the mechanism of transferring these conserved quantities from one place to another. And then it gets
like the accountant.
It keeps track of everything.
Yeah.
And then it makes me wonder, okay, now when you talk about the W, it's transferring electric charge, it's transferring some kind of flavor, and here's the quark that changes from one type to another because that quirkiness has been transmitted through this W to something else. And I have to work my way through that one because this is fairly recent. I probably should talk about things that I've been thinking about for many, many years instead of just the last 18 months. But
this is kind of what we do on the regular, Jason, with our podcast. We are typically sometimes scared to talk about things, but we've actually gotten good feedbacks, to come back to your original question, kind of with being a physics influencer in some sense, where we've gotten good feedback from some of our audience where they like us actually thinking out some of these things.
Kind of working it out in real time.
Yeah. Right. Of course, you have to be careful with a podcast because you just can't have 5 minutes of dead air. Just
let's talk. But only Lex Friedman can get away with that.
Right. Yeah.
Right. Like you have to at least speak a little bit. And if you kind of, speak even your stream of consciousness, and you can try to make it as coherent as possible, that is something that I've noticed people, kind of do latch onto, interestingly enough. And people are kind of tired, I think, of always seeing these real buttoned up,
like polished,
super polished, already have the answer. Every part of the problem has been solved. You don't see any of the humanity. You don't see any of the humanity. And this is one of these things that also makes people more adverse to physics, is because it looks so, when people are relating information this kind of way, it's really nice when you just want to know the information, but it also is really intimidating, because people who don't know the process, they think that this person is just some super genius who comes up with all of these thoughts, in some really short time span, but they don't realize that this person thinks of this one piece of this problem for like a week. They're banking it out with equations, doing it multiple times on a blackboard, screwing up, messing up,
talking to their colleagues,
saying, how does this even make sense? And then they give this magical diamond, that you don't see any of the work behind, and it looks like, wow, that this person's just a genius. Like,
yeah, I can see that. I can see that as being intimidating for someone to think that if you don't come in, like if you don't come in already at the top of the learning curve, then you have no chance. Where I think physicists do fumble and struggle with coming up with explanations. I mean, honestly, like I read some of the Feynman lectures, and I'm like, that's kind of maybe I shouldn't say this out loud, but some of his explanations, I'm like, this is not how I would explain what's going on here.
Right.
It's, people have different approaches. It's not that his explanation is wrong. It's just, if I were to come up with like, what's the most amazingly beautiful description of this property, it wouldn't be the way that he described it.
Right.
And
I know it's not sacrilegious, although Feynman is a great educator. There are, I remember reading some part of his lectures where I'm like, that could have been put way better.
Yeah.
I don't know if it's because the language has evolved or so. Or
well, he was really mechanical in his approach. He's like, if you have a magnet that's oscillating in a field like this, then you're going to get this. So he would go back to kind of like, if I could build this in my basement, this is what it would do, and here's how it would come out. And I don't usually think of problems like torque. When someone talks about a torque with me, I'm like, oh, okay, yeah, force times something.
Torque is messed up. I don't like using torque either. So you're like, what is that? I can't even wrap my mind around that right now. I actually do like Feynman's approach, though, in the sense that he does practical elements. And I think that's one thing that I wish a lot of abstractors would do more of, because sometimes I think theorists tend to lend themselves too much to just coming out with the real deep abstraction. But sometimes it's really hard to even conceptualize what anyone's even saying at all until you have something in reality to hold on to.
Right.
And that's one thing I have to commend Feynman on, is he does like to try to bring it down to earth a lot. And that's something I strive to do as well. And especially as an experimental, physicist, it's helped me to try to ground problems a lot more. So I tend to start from the practical and then build up to the abstract, because it's to me, it's harder to latch on from the abstract to the practical, or from the abstract down,
That's interesting. So I've been thinking a lot about, if I were to teach an intro to high school physics class, maybe mixing both of those into the same lesson, so you can kind of throw a bone out to people who prefer learning it from the bottom up, and then throw another one out to people who like learning it from the top down. So, for example, one of the things that I've just come to realize in some of my live streams lately is I've been going through 8th grade algebra. So I've been live streaming 8th grade algebra the way that I would have liked to learn it. And one of the things that I didn't really appreciate is that what we're doing in physics, so there's math that is kind of understanding how the number line is put together and how numbers relate to each other and what it means to, have numbers in the first place, and how do you do operations on them between different things. And then in physics, where you say, okay, now we're going to assign some physical property to this number line, and we're going to find a different physical property to this other number line. And now we're going to see number line. I don't know if I said that correctly, but I'm going to assign distance on one axis, and I'm going to assign voltage on another axis. And those are number lines that have the properties of real numbers, and that you multiply them and divide them because of all this work that the mathematics people did. And now the physics is mapping reality onto that, and then seeing what happens as a consequence of the rules that exist within physics. And it's really kind of opened my mind a lot more to what it is that physicists actually do, because these are often put, when you look at a math textbook, you're like, when am I ever going to use this? Well, if a ladder's leaning against a house, you can find out what the angle is for the ladder. Right. And that isn't really as engaging of an approach. Okay, yeah, so I can find the angle of the roof of a house or something, but it's not something to run home and tell my mom about.
Right. I mean, some of these things can be. My argument is sort of, well, it's not really an argument, but I'm sort of becoming more of an advocate of contextualizing a lot of this stuff. So humans build these mathematical tools for utility for the most part, right? I mean, there's an argument to be made why calculus became so advantageously used, and what we use it for in certain instances. I love the GPS problems, stuff like that. That gives you some context of what the utility of that would be, like GR special relativity, being used for their context of which problems in which GR becomes relevant.
So are you saying that you present it as, if you were to build this thing, this is where it would go wrong, and so then how do you fix it?
Yeah, pretty much. Like that's a good synthesis of the approach of just, you want to do something, or and this is how I guess we as a community, as a scientific community, agreed that this was the correct approach in some ways. I mean, one of the earliest examples that I think I was given was how you can use sort of the more basic geometry and algebra or trigonometry to do warfare. I mean, as grim as it sounds, that's something that I can see a kid, as sort of violent as that is, like it's still part of human history where these people needed to know how to set over something.
Yeah, and then with that you can say, if you need to launch a cow from inside your city over the wall. But you can also say, if you're firing over the horizon with modern naval warfare, you have to account for the Coriolis force. You'll miss if you don't account for the fact that the Earth is spinning underneath your boat. Right. And a similar thing, because I worked for a year between undergraduate and graduate school at a defense contractor, and they're talking about like all the weapon systems that are out there and that are being developed. And one of them was, you have this howitzer where it would fire several rounds, and the idea was that you would fire them at different angles so that they all landed at the same point at the same time. So you start at a high angle and then thump, 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 and then all the shells are coming overhead and then they all hit simultaneously. And so we did that as one of my problems in one of my physics classes was, okay, let's figure out what are the angles and how far apart do you need to fire them in order to get them all to land at the same point. I mean, it's projectile motion, but at least it's a bit more interesting of a projectile motion problem.
I didn't even know that was, I mean, see, that's a perfect example of like grounding it in some sort of utility, so that it feels more physical and it seems more physical, and also makes it more relevant to certain students. Like they're using this knowledge to do something in the modern world.
So what do you think? Go ahead, Terrence.
I was just to finish off, I think that was the big key is like the context. Like you made the example of the ladder on a wall. Like that's so lame. Who cares? Right? But the context, if you make the context fun and interesting, and just like you said, bringing in real career scenarios. I mean, high school students want to know about the real world. They want to know about, okay, what are the possibilities? Like, what do jobs even do? Like, how does a general, run the military? How does, a doctor perform a surgery? And if you can make these context problems actually cool and make it to like, what is it that you would do if you were in this position or you in this job? That's the kind of things that inspire people, I think, to go down certain career paths and actually take the problem seriously when it's like something that's relevant and interesting. And the latter example, it's just like, you got to beef up the latter example some more, just beef it up. And that's almost makes it worth doing.
Right. Are you saying, let me see if I'll rephrase what you said. If you were to provide the students with scenarios where they have to think more about it than just drawing the picture, they have to think about the complexity of the problem a bit more upfront. And it's not that the problem is so complex that there's no way for them to grasp it, but rather that as they think about it, they're starting to be exposed. They expose themselves through their thought process about some of the challenges that they'll face when they're solving the problem.
100%. Like, you give them the ability to wear the badge if they're a police officer. Give them the ability to wear, the lab coat if they're a scientist. It's like you're letting them kind of role play what it's like to actually be in a job as a real adult, and everybody's curious about that in high school. I was so curious about that in high school. I didn't know what anyone did at all.
What do adults do?
I was like, I don't even know what my dad really does. I don't know what my mom really does. Like, what do these people do? And if you can somehow like give people, give them a morsel of what it's like to actually exist in, the land of adults and solving problems, like that's such a fun and enticing thing in my opinion.
So I'm gonna put this out there, and if you guys pick this up, then I want a piece of the action. But a friend of mine is an iron worker, so he does a lot of commercial welding and things like that. And one of the things, I had him come help me with my backyard fence, and he was talking about in high school he hated doing this and that and the other, and it wasn't until he got out and started his own career that he realized where he would use this stuff. And so one of the things I was thinking of for some high school students, that you can imagine a shop class where you start with some number of points and you have to buy the material with those points, and you have to, in order to make some project, like you're building some contraption, you have to do the calculations that are going to tell how much of this material am I going to need, and then you suffer if you don't purchase enough material, then you can't get the grade. Or if you purchase too much, then you just wasted some of your points. And so it kind of teaches simultaneously the math, the skill, like the craft, and entrepreneurship, about like, if you want to get a good grade in this class, this is the number of points you have to get back. And so you basically sell it. Whatever you make, it gets graded, and then you get that many points more than what you put into it, as a way to advance your grade. I think that didn't happen in my shop class when I was in the 8th grade, but I brainstormed it with him. He's like, that would have been such a cool class.
That sounds awesome.
Yeah, I think we do. Right. I mean, just as also, maybe I should have added this. I in my graduate career, I did a sort of teaching assistantship. I was learning methods on sort of teaching as a service. That's kind of how I approached it. That's my teaching philosophy. We should be doing the students more of a service, to help them integrate a lot of this knowledge, because there seems to be a disjoint, like we were just saying. Right. I mean, the ladder thing, it's like,
it's just like,
who's going to use it?
Yeah. It's so distant from what real life is like, and school seems to just be pushing more and more and more away from actual things that anybody cares about. And it's just like,
so when you're 16, it's like, I'd rather just get a job. And
and you're like, I'm just gonna have fun, talk with my friends, whatnot. I'm just gonna fall asleep to these classes and just hope I can get through it.
And I think also school focuses on, I mean, it was there in my teaching assistantship where I learned why certain things are the way they are. And I'm sure you as faculty, or you understand that, grading is a part, or feedback is a part of the learning process. And so we try to streamline a lot of that by taking even shortcuts in the kinds of problems that we give. I've seen professors just kind of circle problems in a book and just kind of like, I don't know if it's interesting or not, but the thing is, if you ask any physicists, if you have conversations with physicists, they'll try to bring it back or relate it to interesting problems when we're talking about solving problems. You know, I remember a problem like this. I remember this. So the kinds of conversations that we have are steered towards interesting problems. We're always trying to relate it to problems that are interesting. It's like kind of how English majors talk about books, right? It's like, I remember that book. Oh, I read this book. For us, it's about problems.
So what are the problems you think that people would connect with the most? What are the problems that people would be most willing to learn, you know, whatever their nemesis is in math? If
I think it'd be really... Oh, sorry, go ahead.
Oh, yeah, go ahead.
I think it'd be really cool, like, to teach an infinite square well potential problem, just to dip people's toes into what real quantum mechanics is, because every kid nowadays, you know, you watch Rick and Morty, everything is quantum nowadays, you know, quantum computing, but you're just like, when do you ever see this? Like, what is quantum? And if you just dip your toes in just to show them what an infinite square well potential is and why you even solve these, I think that'd just be a really cool, like maybe even a week-long class, because so deep. You can
it's waves on a string. You can do it with a guitar. You can talk about, like, okay, so what are the things, here are the boundary conditions that you get on both sides of that well, which means that the wave function must go to zero with at that point. And then what are the things that fit in that box? There's only certain kinds of waves that will fit in that box. And then you can show them, like, this is how because I teach that class. I teach the third semester of physics for scientists and engineers. And that's how I introduce them to quantum mechanics, is I start with waves on a string, and I say, you know, here's the tower of states that can exist, and nothing else can exist because it doesn't satisfy the boundary condition. So it has, whatever exists within that well has to have a shape that can be a sum of all these components.
That's cool.
That's
but
good
also to remember the context too. I think really what another thing you have to do to make it a full, complete project in terms of conveying how cool that quantum problem is like actually show them, when is a infinite square well potential even relevant? When is quantum mechanics even relevant? Because people don't know even, like, when are you ever using this? Like, show them the actual, like, where this would be used. Like, your cell phone uses quantum mechanical things. Like, it has quantum
like the CCD cameras and...
Right. It's like, actually show them, like, where does this actually come into play? Like, why would we even care about something like this? Who thought, like, how did people even come up with this? You know,
the motivation.
Where did this come from? The motivation behind the problem, I think, is really the piece that a lot of people leave out in terms of quantum mechanics.
I do want to add this, in my assistantship, there was it was funny seeing how every other discipline already contextualizes a lot of, like, what was the motivation of why this thing even exists, you know, or and who did it, or you know, what was the thought process? They cover that, but in physics, that's like largely removed. And whenever I would teach in my lab classes, I would center the question. I would ask questions to the students instead of giving them answers. A lot of TAs beforehand, I guess, were focused more on, this is what you do, this is how you solve the lab. I was trying to motivate them to ask what the purpose of this all is. And so that made appreciably, or the students started to appreciate the class more. And at the end of the semester, they're like, you know, this class was great. I really, really had a lot of fun with this. I didn't think physics would be this interesting, but you made it enjoyable. And that's kind of the thing. Most people that go through physics would, I don't know how many people can say that physics was enjoyable. Because certainly I didn't feel that way going into it in high school, and even through undergrad, it was sort of a bore to go through it. So that's kind of the approach that I would take. I don't know if I'm going to get off my soapbox now. I don't know if
yeah, I think just keeping it cool, man. Always remembering,
keeping
like,
it cool.
Yeah, keeping it cool. Like, just always remembering, like, what are the cool things that you like about physics, and then showing the students that,
Mm-hmm.
showing people what physics labs actually do, what real physics experiments are, all this cool stuff that you really want to know, and then actually relating it to real problems. I think it just does so much for
yeah, I remember. So when I graduated from undergraduate, I kind of assumed I'm going to be a theorist because all the theorists are cool and all the experimentalists are people that, kind of were at the bottom of the class, and they weren't really good. But when I got to school, I learned a couple things. One is the experimentalists are the ones that have all the money, and two is that so I got involved in torsion pendulum experiments, where the one in particular was measuring the inverse square law, verifying that the inverse square law holds at different length scales. And so, but then I learned all of the details about how many things you have to consider when you're building an experiment. You have to worry about the fact that the laser's hitting right here, and so you're going to have a hot spot on your mirror at that point, and so the ballistic trajectory of the residual gases are going to bounce off at higher velocities from that spot than they are from somewhere else, and so that's going to introduce a torque onto the system. And all the experimentalists get to actually touch more physics than the theorists do. The theorists kind of focus on one thing, but when you actually need to build something, you have to worry about what's the capacitance between two wires that are next to each other. And so it really, when you gain an appreciation for what the experimentalists are going through to make sure that something functions, it really makes it, I think, a more rich problem to work on. So when I was at Fermilab, I mean, most of my research is in exoplanets, so I'm studying dynamics and things like that. But at Fermilab, I was able to run an experiment on chameleon dark energy. But it involved, vacuum systems and cooling systems and laser systems and data acquisition. And when you get that kind of breadth, that you have to know something at least well enough to be able to meet your design criterion about, how closely can we time all these different things. It was, how do you measure the shape of the pulse of a laser beam, where if that laser beam pulse were to actually hit your detector, it would destroy your detector in one shot?
Right. Oh, this sounds like Frog. Did you use Frog?
No.
Nick? Okay. Because I know that they measure pulses using something called Frog laser pulses.
Mm-hmm.
It's just a cool technique. Yeah, this was something I've worked on before, and it just reminded me what you were saying there.
Yeah, a lot of there's a lot that goes into sensor building, and I think that's also a big component for theorists. Just like they say, we need these parameters. A lot of it dilutes to, even though you have these abstract hypotheses that need to be tested, you do need to integrate them with experimental work. So that's kind of where that hypothesis meets. I wouldn't say reality, but the constraints of engineering, right? Constraints of engineering, budget, all this stuff.
So let me put out a topic that, and you tell me if you think this is something that would catch on in terms of, like, if you're a high school student, is this something that would engage you in several units of physics? And that is the electric grid and how to supply electricity to the country.
Oh, heck yeah. I'm already into it. I'm already in there.
That is a cool problem.
Yeah, because it's so mysterious. When you're a kid, you're like, how does any of this stuff even work? That's just so cool. That's a cool one.
Yeah.
So
power line.
Oh, go ahead.
Sorry. No, I was going to say power
every
line.
day, and you're just like,
well,
I guess
there
that's
they
something.
are. Yeah, that's something.
That's how the electrons get into the house.
Right. Yeah. Right. And then you learn, well, that's technically
not even that deep. You're just like, it's there.
And then even then, a lot of the perceptions of what they are wrong.
Right. So you got the idiot guy down the street telling me, yeah, man, the government, they try that.
That's how they listen in on you. They buzz in. Yeah. That buzzing noise, that's all the telecommunications going through the lines. No, but in all seriousness, it's you have, I guess, a true student of physics is trying to figure out what the world around them is, and try to find sort of the best model approximations to that. And let me just say this: the one time I was really impressed with a human being was in my graduate school, was a professor sitting in a meeting with us, and I don't know if it just came to them, but they started describing everything in the room in the language of physics, like
That's awesome.
why the light, bounces off this way, why the color of that is this, the photon emission here, and then they knew like the amount of voltage that's going through the walls, like, they literally knew everything about the space around them. It blew my mind.
It's like the rapper, when you call out the different letters, they just start rapping with every letter.
Right.
It's
sort of like somebody showing you the Matrix, and you feel like Neo kind of,
right.
In that moment, where you become awakened at the power, and at that moment, I'm Neo. I'm starting to believe.
Right.
I'm starting to believe in the power of physics, and it's sort of like, we do have to have good professors that sort of have a beacon of like, do you want to see a cool trick? And it's the sort of magical elements of reality that sort of seem like you're looking behind the veil. The magician is showing you the trick, and it's just as fascinating as the trick itself.
Yeah, so this is my first lecture, is a 58-cent can of corn. And I talk to my students about what does it take to get a 58-cent can of corn into a giant refrigerated box in the middle of the desert.
Awesome.
And
that is a great question.
So
sick.
And how many hours of engineering time does it take to design the can? It has these ridges in it, and why are the ridges the shape that they are, and why is the can made out of the stuff that it's made out of? And when you mine the ore, you have the safety equipment, and people had to think about, how do we make sure that the miners have toes at the end of the day? And and so I go through and I kind of use it hopefully to inspire them to do a good job, because these are people that are going to be building the bridges that I'm driving over.
Yes.
But the world is built, the amount of engineering time that goes into making something. And I also talk about, how much engineering time has gone into making a pane of glass, and how easy it is to break that glass. It's real easy for some schmuck to walk down the street with a hammer and just break a bunch of windows and think that he's doing something meaningful. But the amount of time and energy that's gone into making glass in the first place, that you can order and put into a window that can withstand, whatever, it's significantly more challenging. And I just tell them, look, there's a bunch of people on this campus who think that they're going to remake the world, but they can't even change their own cell phone batteries. And it's going to be up to you guys, you men and women in this classroom, to actually make the society function. Because if you want to feed 8 billion people, it's going to be because of engineering. It's not going to be going back to chasing bunnies with sticks.
Exactly. Yeah.
That's amazing.
Yeah.
And also, that glass thing is a great allegory for just like how difficult it is to build rather than destroy. Like, it's just so simple to live your life destroying things, but it takes so much more responsibility and effort to build. And it's just
you're saying there's
interesting. There's so many lessons to learn.
You're like, there's moral,
that whole little area you just spoke about.
Moral lessons in physics,
right.
Entropy. Entropy is more than just a physical.
Right.
Yeah. Well, and a lot of times people invoke physics as a reason to justify their own. It's like, oh, we learned from Einstein that everything is relative, and it's like, well, actually, we learned from Einstein that there are certain things that are invariant, regardless of your point of view.
Right.
Yeah.
Right.
Facts still exist. So, yeah.
The speed of light will be there whether you like it or not, and it doesn't matter what perspective you want to take on the subject.
Exactly.
Yeah, those are all important things. I don't think it's a coincidence also why certain people that are in this discipline, like physics, have, I would say, a certain sense of spirituality to them, sort of appreciative sort of mentality of the world around them. I don't know if that's a character disposition that sort of directs you towards physics or something like that, but yeah, I have noticed that.
Yeah.
Anyway.
Well, I know that you guys are both on a schedule, so I wanted to just let you know I really appreciate your time. This was a good discussion. Maybe we should do it again sometime in the future.
Sure.
Any last comments that you'd like to say to the broader world? Yeah,
physics needs their Moby Dick prop.
Physics needs their Moby Dick.
Yeah.
unpack
like
that.
the story. No, I can't unpack that now.
Oh.
But
Sounds a little bit too vague.
like a story, like a
mean.
great story of like searching for answer and meaning. Like they're that needs to captivate the world as good as Moby Dick did.
Okay.
Yeah.
I think Sagan has done some of that. Carl Sagan.
Mm-hmm.
Yeah, he did a pretty good job.
So are you
That's
saying
true.
that like physicists you're saying that in order to produce an inspiring or in order to inspire someone to become a physicist, they need to have something that they are willing to chase to the ends of the earth to get to the bottom of.
There we go.
Yes. I was trying to steer you towards that. But
okay.
Thank you. You got it.
He helped you out on that one.
So, so that's one of the things, like I mentioned with the electric grid, that's one of the things that I'm putting together for this professional development class is, what is nuclear energy? What does it take to make nuclear energy? Why would we use it? What about these other things? And what are the upsides and downsides of all these things? And my current class that I'm teaching this semester, which is an energy class, our next unit is going to be on the Green New Deal. And everyone's going to read it, and I will get their feedback. I'll say, you go home and read it, and then we'll talk about it when you come back.
I want to add something.
I wish I had your class.
That there was one of the most rewarding classes I ever took in my undergrad was the senior level class, where it's a graduation requirement. So before they send you out to the world, it's essentially a professor cleaning up any misconceptions that we have about physics. So it's sort of like an open seminar where we ask questions. What topics do you want to know about? Hey, we didn't really understand this thing. And I mean, there's still a lecture format. So if the students don't have anything to ask, he proposed interesting scenarios or paradoxes that would help clarify your thinking. For instance, classic special relativity problem, the twin problem. And then there's also the EPR paradox, spins and stuff. And he helped clarify a lot of things there too. But that class it didn't really focus on the math. It focused on the concepts and integrating that information that you learned in the past 3 years.
That would have been really useful for me too. Because otherwise I had to learn it a decade after I'd already graduated. It's like, oh, that's what I did. Now I know what I did when I was in modern physics.
Isn't it funny how much you're just cleaning up knowledge after you're out of school? You're just cleaning up all of the stuff that you didn't understand. And you're like, man, I didn't understand anything.
Well, let me ask one more question if you have time. And that is, with your peers from high school at different stages, at what point and under what circumstances, if you know, did they leave math or physics behind, like STEM behind, and like, this wasn't really my thing? Like, what was it that were the bifurcation points that separated people, perhaps prematurely, in their choices for what they did with their education?
I can answer that one really fast. They were pretty much all distilled to socioeconomic problems. So it was their status as, like, I had one friend his dad was very wealthy, but his dad was like a nuclear engineer or something, and he just kind of let him pay for college, and he was like, I can't pay for this, is too expensive to survive off of. And so he had to leave physics behind, and he still found a way to end up back at physics, but he still hasn't fully completed the education. And I know a bunch of other students that, at least in high school, there was like a couple that I knew that were under economic constraints to like have to provide for their family. So a lot of it was not because they were just like, whatever, this stuff's boring. They already had an interest in it. It was mostly other, how would you say, other
factors.
Yeah, other constraints, other factors.
Yeah.
Like life happened and.
Right. Yeah. I feel like my physics graduating class, the people in that sector who left and didn't go back to physics, it was just down to couldn't get a job in physics, It was just like, I have to find a job now, and it has to be something. So let's just find something. You can't always get what you want, and my institution was not like a super prestigious institution. It was decent, probably like a little like an average institution. And that's just what happens. Life comes, and it's just like, I can't just stick around waiting for some job related to physics, especially if you only have a bachelor's degree and you have to, work in finance or something something like that.
Right. Yeah.
You have to make a bunch of money now,
Yeah. Well, so that was, when I did software engineering, because that's what I did for the defense contractor, there was only one computer science person on our whole team. Everyone else was mathematics or physics. Wow. I really enjoyed it, working in that industry, but I didn't know going in that was even a possibility. I was like, well, if I major in physics, I can either teach college or teach high school. Those are my two choices. And so what are the exit ramps is something that I think is sorely lacking, even in astronomy, maybe even more so in astronomy, where there's no good career off ramp. They're trying to fix that, but it's fits and starts, and it takes a decade for them to kind of wrap their head around, okay, what's the right way for us to get people out of academia and into something without having to go through a big midlife crisis about, oh my God, I failed. I need to go find a job. And then they get out and they're like, wow, why did I wait so long?
Yeah, exactly.
Yeah. No, I see a lot of astronomy students that go into programming, some kind of data science.
Data analysis
stuff. Yeah. Astronomy is where all the cool people are at. I tell people, physics and astronomy, it's weird. I don't know why they still have a huge differentiator. I mean, they definitely treat them differently, but all the cool people I met,
they take all the same classes.
Yeah.
I don't know.
As an undergraduate, you take all the same classes. There are some differences. It depends on if you're talking about like old school astronomers that care about the width of the ytterbium line from some spectrum that they took with some telescope, as opposed to like the cosmology side, where high energy physics has basically come in and said, okay, it's time to go, time to do big boy science now. We're going to industrialize this process, and we're going to build, a $100 million survey to do something. Or in the case of what's coming up, the Vera Rubin telescope, or like LSST, where it's, here's a $5 billion program. A lot of astronomers don't know how to spend that kind of money unless they're on NASA, but high energy physics is like, oh, $5 billion. Yeah, well, here's what we can put together for something like that.
We've already got it written up right for you. But
but I think that's about it for me.
All right.
Yeah, excellent. And I guess just a final plug for us then. If you guys are just tuning into us and aren't aware, we have a podcast, physics podcast. Unfortunately, you're a little late if you hadn't noticed, if you don't know us, because we're winding down. Things are evolving, but you can check us out at Eigenbros on YouTube. We're also Eigenbros pretty much everywhere, like Spotify, wherever you want to listen to podcasts.
Let me add this, because it's not a huge disservice. We have a back catalog of about 150 episodes.
Right.
And we've had pretty good guests. We've had Veritasium, 3 Blue 1 Brown on some smaller content creators that we think are really great. Dietrich Labs was one of the recent ones.
Right. Mithina Yoganathan.
We
can go on.
Yeah, I mean, you can go through the list. We just had the guy who helped invent the warp drive.
Right. That was cool.
Yeah.
So just check out our channel and subscribe, like, share, comment, all that good stuff.
Mm-hmm.
We wouldn't be a YouTuber if we didn't say all that.
And
I think that's it. And stay tuned for your boys in the future, I guess.
Yeah.
All right, sounds good. Hey, thanks you both for coming on. I really appreciate it.
Yeah,
we appreciate it, Jason.
It was a pleasure.